Make sure you read through the notes before watching the video so you can get familiar with all the definitions, because I'm not going to cover those as we go through since you do have access to this blank document. All right, so moving into converting between degrees and radians. So here's your formula for getting back and forth between the two units of measure. Degrees, units, the little, either the word degrees or the little degree symbol up in the exponent-ish area. Radians are unitless. You can put rads at the back if you want, but you don't have to put anything. All right, so we're converting between the two. So we are given a 45-degree angle and asked for the equivalent radian measure. So what we want to do is get out of radians. So we're going to take our, or get out of degrees and into radians. So we will need our degree units to divide out. So the equivalent degree measure is 180, 2 pi radians. And then we do a little math on this. We do 45 divided by 180, reduced form, gives us 1/4. So we typically would write that instead of 1/4 pi, write that as pi fourths. B, 330 degrees. So we're taking our 330 degrees and getting out of the degree measure. So that means I need my degrees to divide out. 180 degrees and go into radians. So we take 330 and divide it by 180, and its lowest form is 11, so 11 pi 6. See, 2 pi thirds. This unit is in radians, and we know that because the word degrees nor a degree symbol is not given. Radians are unitless, so nothing needs to be there. So that means I need the radians to divide out. So the equivalence is going to be pi in the bottom and the degree on the top, because that's what we're trying to get into. So we're going to do 2 times 180 divided by 3, and that gives us 120. Must have the degree symbol on there. For D, negative 8 pi thirds. So we get our angle negative 8 pi thirds in radians. I need my radians to divide out, so pi goes on the bottom, going into degrees, so 180 degrees on the top. So negative 8 times 180 divided by 3 gives us negative 480 degrees. Example 2, it's still converting, but notice the directions have changed. Give your answer rounded to 3 decimal places as needed, so make sure you pay attention whether you're giving a decimal answer or you're giving an answer. Usually it will say in terms of pi as the last one. Watch the unit. So 2, that is not a degree angle because there is no degree symbol. That is a radian angle. So I need the radians to divide out. So the pi is going on the bottom and the degree 180 is going on the top. So we're doing 2 times 180 dividing by pi because we're giving our answer in decimal forms called decimal radians. That gives us 114 to 3 decimals, 592. And again, when we're going into degrees, it's got to have the degree symbol on there. 5.1 degrees, getting out of degrees, so the 180 on the bottom, into radians, pi on the top, but we're doing the decimal answer, so I need 5.1 times pi divided by 180 to 3 decimals, 0.089. And typically decimal radians, we'll write rads at the back just so we're reminded what we were measuring in, but you don't have to. Pi 17ths is in radians. So pi over 17, pi's got to go on the bottom into degrees, so the 180 on the top. So 180 divided by 17 in our little handy dandy calculator, 10.588 degrees. And finally, negative 76 degrees. We want out, so 180 on the bottom, into radian, so pi on the top. So negative 76 times pi. That divided by 180 gives us negative 1.326. And I'm going to go ahead and put rads at the back. All right, going a step further, so drawing angles in standard position. Here is your standard grid when we're measuring angles. Notice the axis of rotation is counterclockwise. Counterclockwise is a positive angle. Clockwise is actually how we measure negative angles. So there's your axes depending on whether you're measuring in degrees or radians. All right, we're drawing example 3. Draw each angle in standard position. Determine which quadrant the angle terminates in. That means which quadrant does it stop in. Quadrant numbers, if you recall, go counterclockwise as well. Quadrant 1 is plus plus. Quadrant 2 is when x is negative, y is positive. Quadrant 3, both x and y are negative. And quadrant 4, x positive, y negative. All right, so determine in which it terminates. Do not convert back and forth. So what that means is if the angle's in degrees, you need to stay in degree mode. If it's in radians, stay in radian mode. All right, so first thing I'm going to do, we're drawing it standard position. So I'm going to go ahead and get my XY axis drawn. And I'm going to get my labels on there. So in degrees, so that means I need to stay in degrees. So get familiar with your labels. 0 degrees, straight up 90 degrees, straight left 180 degrees, straight down 270 degrees, and then we come full circle 360 degrees. So an angle of 120 degrees, an angle starts standard position is out the positive x-axis, and then it either rotates counterclockwise if it's positive or clockwise if it's negative. So we're positive, so we're rotating counterclockwise. So 120 degrees, we're going to be swinging counterclockwise, and 120 is in between 180 and 90. It's a little closer to 90, so that's where I'm going to stop it. So here is my angle in standard position, and it terminates in quadrant 2. I copy my x and y axis. All right, example 2, my xy axis. This one is in radians. It's also negative. Okay, so I'm going to go ahead and label your standard axis in radians. 0, no degree symbol here. 90 degrees is equivalent to pi half radian. 180 degrees, if you convert it, is pi. 270 is 3 pi halves. And then 360 is 2 pi. So if we always start positive x-axis, so there's our initial ray. This one is negative, so we are swinging clockwise. So if you wanted to label it clockwise, you could. So I'm going to go back now and show you what the equivalent would be. So if pi half is the first axis straight up, if we're rotating counterclockwise or clockwise, negative pi half would be straight down, negative pi would be to the left, and then negative 3 pi half straight up. So basically just your top and bottom switch when we're rotating negatively. So we're looking for negative 5 pi force. So if you look at your measures, that's bigger than pi, but it is not bigger than 3 pi over 2. So that means 5 pi force, negative 5 pi force is going to be in here. And then again, to show the correct directional rotation, we draw that clockwise, kind of a terrible arrow, but clockwise rotating arrow to show that we're talking about the negatively rotated angle. And that one terminates in quadrant 2. So quadrant numbers do not change just because we rotate in a different direction. C, negative 230, so we're back in 2 degrees. So I'm going to label my axes in degrees. So we've got our 0, full circles, 360. You can go ahead and list them both. And we've got 90, 180, and 270. So this is a negatively rotated angle, so it's the same idea when you're in degrees. Basically, your tops and bottoms are just going to switch. Straight down is going to be negative 90, straight left becomes negative 180, and then up becomes negative 270. So initial ray, and then rotating clockwise, so we're swinging down and around. So negative 230, this would be negative 270. So negative 230 somewhere in between here. We'll just put it there. And then again, make sure you get that arc and arrow to show the direction of rotation. Without that, I don't know what angle you're talking about. So make sure you get the direction on there. Look at this, we're in quadrant 2 again. All right, 16 pi thirds. So we are in radians. All right, in sketching an angle like this, I'm going to go ahead and do the initial sketch with your reduced angles. So we've got our 0, full circle is 2 pi, then we've got pi half, we've got pi, And then we've got 3 pi half. So when it's not as obvious where the angle lies, sometimes instead of labeling our axes the way I just did, it's better to label them in terms of how you're counting. So like by pi thirds. So I'm going to put the equivalent label in terms of what this angle is being counted by, which is pi over 3. And I'm going to do those in pink. So for me, easiest way to start it is to, I like to go full circle. How many pi thirds is 2 pi? Well, it's double. That is the unsimplified form. Why is that? The pink is really thick. Let me lighten it a little bit. Let's go down to 1. There we go. So the equivalent for 2 pi is in pi thirds would be 6 pi thirds. So think unsimplified angle. 6 divided by 3 is still 2. It's just easier to see it because that's how we're counting. So full circle, 6 pi thirds. So that means a half circle is half of that, 3 pi thirds. Let me get that. 3 pi thirds would be here. Half of that would be straight up, so that would be 1.5 pi thirds. And then if I take the top and the left one and add them together, that gives us the bottom, which is 4.5 pi thirds. So one thing you want to notice with this one, so we've got our positive ray always in the same spot. Notice if I go full circle, so if I start to draw this angle and I go all the way around, I'm only at 6 pi thirds. I haven't made it to 16 yet. So this is what's called an over-rotated angle. When the angle has been over-rotated, the easiest thing to do is to get rid of those full rotations until you know where to stop. So I'm going to take my 16 pi thirds angle and I'm going to take a rotation away. A rotation in terms of what we're counting by is 6. So I'm going to take away 6 pi thirds of it and see if I can get it down to a single loop yet. So if we take 6 away from 16, that gives us 10. 10 pi over 3. So if I notice 10, 10 is still not smaller than 6. So that means we have an extra loop on here. So I'm going to do it again. I'm going to take my 10 pi thirds and I'm going to get rid of another full loop, which means another 6. And that gives me 10 minus 6 is 4, so 4 pi thirds. 4 pi thirds is smaller than 6, so I can use this to figure out which quadrant we stop in. And then because we got rid of 2 full loops, that means when we draw our arc, we're going to make 2 extra loops on it. So I start rotating counterclockwise, and I'm looking to pass 4, so there's 1.5. There's 3. If I pass this one, I go to 4.5, so that's too big, so we're stopping at 4. So our angle stops in quadrant 3. Difference being is it's going to make 2 extra loops. So rather than drawing it like we did the others and stopping directly on that terminal ray, we are going to loop around. So we're going to go, there's 1 full loop, and then we're going to spiral it out. There's our 2 full loops, and then we stop here. So you kind of get a little dizzy looking at it. Okay, so if it's what's called an over-rotated angle, you just make extra loops before you stop on that terminal ray. And the number of extra loops you make depends on how many full rotations you took out. So we took out 1 full, we took out 2 full. So that's why we made those 2 full loops around. But we still terminate in, I'll put it down here, terminate in 1, 2, 3. All right. Finding coterminal angles. So coterminal angles, the definition is right above example 4. There are 2 angles that start and stop in this same place. So going back to these examples where we drew the angles, that's why I said make sure you show the arc with direction, because like if we look at this example 2 here, I could have drawn this right there. Those 2 angles I just drew were coterminal because they both started on the positive x-axis and ended in the same place. So coterminal angles are angles that are 1 rotation away from each other. So either 360 degrees or 2 pi radians. All right, find the coterminal angle that is between 0 and 2 pi, because both of these are in radians. All right, so easiest way to do this, you can draw a picture if you want to, but it's not necessary. We need to get rid of full loops. So what I want to do is note what I'm counting by. So we are counting by, I like how thin my little pen is. I'm going to go back up to 2. Okay, 2. So your count by is your units of pi, pi sevenths. So we are counting in terms of pi sevenths. A full rotation we know is 2 pi, but just to make the fraction math easier, I don't want to write it as 2 pi. I want to write it as pi sevenths, which means always double. So instead of doing the typical 2 pi, just to make our fraction math a little bit more manageable, it is 14 pi over 7. That's still 2, it's just the unsimplified form. That makes the math a little bit easier to handle. All right, so to find our coterminal angle within one rotation, that's what this restriction is right here, I need to get rid of full loops until I can no longer do that. So we're worried about that 19, so I'm going to focus in on the 19 from our numerator. I have 19 units of what I am counting by. I need to figure out how many full loops I can get rid of. Well, we can look at that angle right there and say 14 is easy to get rid of. So we are going to remove one full loop. So 19 minus 14 is 5. Since 5 is in between 0 and 14, we have our answer. We just need to put our units back on there. So our coterminal angle would be 5, and then you put your count by back on pi sevenths. So all we've done is just eliminate the unit of count by, the pi sevenths, just to make the math a little bit faster. So these two angles are coterminal. They start and stop in the same place. The difference being that 19 pi sevenths went around the loop one extra time from the 5 pi sevenths before stopping. Negative 29 pi sevenths, so we're still in radians. So we are counting by pi fifths. So I'm going to focus in on just the number in front in a minute, the negative 29, which means our full rotation in terms of pi fifths is going to be 10 of them, because 10 divided by 5 is still the 2 pi. Okay, we're just thinking about it unsimplified to make this angle more manageable to deal with. So in this case, we have a negative angle. So instead of subtracting full rotations, we want the positive angle. So we are going to add full rotation. So I'm going to take my negative 29 and I'm going to add 10 to it. If I do negative 29 plus 10, I'm going to get negative 19. Negative 19 is still negative. So then what we want to do is we just want to repeat this process until we find it. So we can continue to add and add and add, which is fine. But once again, if that angle is too big, that's going to cause a problem. So instead of just adding on full loops, we could just go straight to, well, how many can we deal with? So this time I'm going to divide. So I'm going to take negative 29 and I want to divide it by a full rotation, which is 10. So if we do negative 29 divided by 10, that tells us that we're going to make 2 full loops, and then we have that 0.9 extra. Okay, so we're not concerned with those full loops. We are only concerned with the decimal part of the loop. So then I divide it by a full rotation. I am going to remove those full rotations. The integer is not important, so we're going to remove it by adding 2, just to get the decimal by itself. And then to figure out what part of the way we go around, we are going to multiply it back by what represents a full rotation, which in this case is 10. So we're going to divide by that full rotation, remove the integer because that's the full circles we make. Then we're going to multiply back by a full rotation to get the decimal value, which is going to give us a negative 9. So now that is the first coterminal angle that is negative. We want the first coterminal angle that is positive. So now we're going to add a loop. So now we're going to add 10. I like to keep them in the same order. So if I take negative 9 plus 10, I'm going to get 1. And then we just put our count by back on there. So pi fifths would be our coterminal angle. So you divide by a full rotation. Get rid of that. Remove the integer, multiply by a full rotation, and if it's negative, add a full rotation. If the angle was not negative, we would be stopping right there, and that would be our answer. So we can apply this same process on that last one. It's just that last one was only within one rotation, so subtracting 14 once is easier than going through this division multiplication process. All right, coterminal angle in degrees, so the exact same process we just did, but now we're moving into degree measures. So 455, this time we don't have to worry about a count by or anything because degrees are degrees. So 455, we can look at that compared to 360, and we know that is not over-rotated by much. So the easiest way to find our coterminal angle here is going to be just take the given angle, subtract the single loop because we know that's all that's missing. So we're going to do our 455 minus 360, and that gives us a 95-degree angle. So there's our coterminal. When it's within one, you either take off a loop, or if it was within one negative, you would just add a loop. For B is a little bit bigger, negative 832. So I'm going to do a similar process to what we did with B in the radian example previously. So I'm going to take my angle, and rather than sitting there and adding and subtracting 360 over and over and over, I'm going to go through the division process this time. So this time we're going to divide by a full rotation, but in degrees, that would be 360. So we're going to take our negative 832. We're going to divide it by 360, and that's going to give us a lovely decimal, negative 2.3-ish, 311-ish. So that's telling us we're going to make 2 full clockwise rotations since it's negative. We don't care about those 2 full rotations, so I am going to get rid of them. I am not worried about the 2. So I'm going to add those back, and that is going to give me negative 0 point, and then that 311 stuff. And then same process as the last one. Now we're going to multiply back by a full rotation to figure out where to stop on that partial. So we're going to times 360 degrees. Make sure you use the entire decimal so you don't have any rounding error. So we're going to multiply by 360 degrees, and we get negative 112. And because it's negative, so again, when you start negative, when you do this process, you get the first negatively rotated angle. So to get the first positively rotated angle, add a loop. So we're going to add 360 onto this angle, and we get 248 degrees for our coterminal angle. So exact same process we did in the last example, just in terms of a full rotation in degrees instead of in radians. Divide by a full rotation, remove the integer, multiply by a full rotation, and if it's negative, just add a loop. All right, applications. So just a couple of applications involving angles. So there's your formula for arc length. Most important thing for the formula of arc length is that angle is in radians. If it's not in radians, you must convert it to the equivalent radian measure, or you will get the answer wrong. All right, easiest way to think about an arc length is to think about a slice of pizza. If you have a slice of pizza, the arc length is represented where the crust is. It's like a chunk of the circumference. So this is Johnny, example 6. Johnny just ate a slice of pizza from Big Lou's in San Antonio with a 40 degree central angle. If Big Lou's pizza has a diameter of 42 inches, find the length of the crust, arc length, Johnny just ate. So, all right, formula for arc length, S equals radius times theta, where theta is the radian angle measure. So if we read what we're given, word problems, the words matter, has a diameter of 42 inches. Remember, a diameter of 42 is not your radius, that is double the radius. So the radius is half that diameter. So your radius is going to be half of D. So if we take 42 and cut it in half, we have a 21-inch radius. And yes, I did look up, that's the size of their pizza. So we have a 21-inch radius. So to get my arc length, or length of my crust, I take my 21-inch radius. We have a 40-degree central angle. Central angle just means it's from the center, which is what we need. However, it is in degrees. If you use degrees, it is wrong, so make sure you get it converted. We're going into radians, so the pi goes on the top, out of degrees, so the 180 goes on the bottom. Notice the degree symbols are going to divide out with each other. All right, so there's 2 ways you may be asked for this answer. 1, exact, which means in terms of pi, or 2, rounded to the nearest 1, 2, or 3 decimal places. So we'll do both. So we're doing 21 times 40, and then taking that and dividing it by 180 in lowest fraction form is 14 pi thirds. So if they said, what is the exact arc length? This would be your answer. I'm not really interested in that because that doesn't really make a lot of sense to me. I don't know how long that is. I want it where I can kind of see it. So if it says give your answer rounded to the first, second, or third decimal place, we would do similar with the angles earlier, just multiply everything out. So 14 times pi, and then whatever that is divided by 3. And we get 14 point, I like 3 decimals, 661 inches. The units of the arc length will match the units of the radius. So he ate a slice of pizza with nearly a 15-inch crust. It's kind of crazy. All right, more applications, angular and linear speed. So I give you the formulas for angular and linear speed. However, I don't use these because it's just one more formula to try to remember. Instead, I just use the unit conversion. So just getting, if I'm in inches and I need feet, I get out of inches using the relationship between inches and feet and just keep going until I'm where I need to be. Okay, so there's your formulas if you'd like to use those instead. To me, it's easier just to use the stoichiometry. All right, example 7. A wind turbine with a 120-foot diameter makes 22 rotations every minute. Find the linear speed in feet per second and the angular speed in radians per second of the turbine. So angular speed is the speed at which the angle is rotating. Linear speed is a linear unit of measure per time. So angular measure per time, angular speed, linear unit per time, linear speed. Make sure you know which one it is you're looking for. Angular speed will always be in either radians or degrees per some unit of time. All right, so let's go with, it says linear speed first, so we'll start with the linear speed. This is going to be my work for linear. So the key for both is you need some sort of ratio, and the ratio that we need to start is this rotations every minute. Rotations or revolutions per a unit of time is going to be your starting point. So we are making 22 rotations in 1 minute. So that's going to be my setup. 22 rotations or revolutions, they're the same thing, every 1 minute. So here's our starting point. So for linear speed, if we go look at what our goal is for linear speed, our goal is feet per second. I like to fix my time first, so I got to get to seconds. So if I look at my time, I'm in minutes. Minutes have to go. So in order to get rid of minutes and make them divide out, I'm going to put them on the top. Since minutes are directly related to seconds, I'm going to go straight into seconds. And there is 1 minute every 60 seconds. So right there, I can look at my unit division. Minutes are gone. My time is fixed. I'm in seconds. So now what I've got to do next, I've got to get out of rotations and into, for linear speed, into a linear measurement. And the key here with linear and rotations, to get out of rotations and into linear, use the circumference. So you're going to use the circumference of a circle, which is the formula 2 pi r. Okay. So rotations, I want out of rotations. So that means they're going to go on the bottom, since over here on my ratio, they are on the top. So 1 rotation, I am going to go into a linear measure using the circumference, and the circumference units will match the units of either the radius or the diameter. And if we read the problem, the diameter is in feet. So that means I am going to go into feet as well. That one's too thin also. Why are these thin? No, it's not. Just writing funny. Zoom in a little more. There we go. So we're going to get out of rotations and we're going into feet using the circumference. Circumference is 2 pi r, or if you'd rather think about it in terms of the diameter, depending on how it's given, it's pi d. So since we're given diameter, I would probably look at the pi d one. So 1 rotation is the distance all the way around our circle, which is going to be 120 pi feet. So then if I look at my stoich, my rotations are gone and I am now in feet. Let me go check what we're supposed to be in. Linear speed in feet per second, and if I check my units, feet per second. Everything matches. So now I just need to multiply everything out on the top, multiply everything out on the bottom, and then divide the 2. So if we go to the top first, 22 times 120 is is 2640, and we're just going to slap the pi at the back. Over, multiply everything on the bottom. Well, it's 2 ones and a 60, so that's going to be 60. And our units are feet per second. Let's make that bar a little bit longer. So again, double check your work for your answer. You may be asked for the exact speed. You may be asked for the decimal speed. So if you're asked for the exact, we're just going to slap the pi at the back on the reduced fraction. So 2640 divided by 60, which actually divides nicely, into 44. So exact answer would be 44 pi feet per second. If it says give your answer rounded to whatever decimal place, we just need to multiply that out, which would be 138. Like I said, I like 3 decimals. Read online assignments very, very carefully. 0.230, because it's 2 zeros, feet per second. So the reason I like the decimals is because it gives you a little more explanation as to how fast it really is moving. All right, angular speed. So angular speed, or our goal is radians per second. So we're going to start with that initial rotation, that 22 rotations every minute. So we've got our 22 rotations each minute. So we still have to get our time converted. I think, let me go double check. What was it? Radians per second, yeah. So we're in minutes. I still got to get out of the minutes. I'm going to do it in the exact same way we just did. Minutes, got to go. Seconds are coming in, and it's 1 to 60. So I can see my time's fixed. Now I got to get out of rotation. So there's 2 ways in and out of rotations. One, a linear measure using the circumference like we did up at the top for the linear speed. 2, using angles for the angular speed. So for this case, we're going to use the angles. So I have 1 rotation, and you have 2 choices on the angles, either degrees or radians. Because this says radians, it's kind of pointless to go into degrees, so we're going to go into radians. And for 1 rotation, it covers 2 pi radians. So the nice thing about this conversion, it's the same every single time. It's either 2 pi radians or it will be 360 degrees, depending on which you're asked for your answer. So if I check my units here, radians per second, we're good to go. So then we just math it. So across the top, 22 times 2 times pi. It's going to be 22 times 2. 4 pi. And then we have our, oops, I forgot my pi. Denominator, not feet, radians. Get my units right in the middle. It's a very strange looking pi I wrote. And then denominator, 1 times 60 times 60, 60 seconds. So exact would be the 44 out of 60, lowest term. So 11 pi 15ths for the exact answer in radians per second. For the approximate answer, we would just take that times our pi, and that gives us 2.304 radians every second. Next. All right, on a carousel merry-go-round, you know, the little thingy that goes around and around, you always ride on some like creepy animals. The outer row of animals is 20 feet from the center. The inner row of animals is 10 feet from the center. The carousel makes 2.5 revolutions per minute. What is the difference in feet per minute of the linear speeds of the animals of the outer and inner rows? Give your answer rounded to the nearest tenth. And then what about their angular speeds? We got a lot going on here. So outer versus inner. So here's just kind of your visual. Here's my sad little merry-go-round. And then here's the inner. Whoa, what is that? Try again. There we go. There's my inner row of the merry-go-round. And then there's the center. All right, so let's go with outer first. So as far as the outer row, so on the outer row, it says they are 20 feet from the center. So 20 feet from the center means that R is 20. Okay, so let's get the linear speed for the outer row first. Carousel makes 2.5 revolutions per minute. There's my starting ratio. So I am making 2.5 revs or rotations. They mean the same thing. That's a crooked division bar. Every 1 minute. So let's go check our units. What is the difference in feet per minute? So feet per minute, my minute is fine. I don't need to adjust my time. I just need to get to feet. So let me go ahead. That was in feet. So I've got to get out of the revolution. I don't want to be in a revolution. There is 1 revolution every circumference of your circle. So the circumference of a circle, recall your formula, 2 pi r, since this one's in terms of the radius. And the units of our radius are feet, so that means when we do this circumference, it is also going to be in feet. So 2 pi times 20 feet. So 1 revolution is the distance all the way around the edge of this carousel or merry-go-round. And then if I check my units, I'm in feet per minute. So that's all I got to do. So then we just need to look at this. So my answer, it says our final answer is being rounded to the nearest tenth, but we will do that at the end. So right now we've got our 2 points. So denominator is 1, so we need 2.5 times 2 times 20. We'll put it in terms of pi first so that we don't have any rounding error in between. And we get 100 pi feet per minute. That's how fast the outer edge is going, the outer row of animals. So now let's go check the inner row. So I'm going to do a little break right here. So exact same thing, but now we're going to deal with the inside. All right, so the inner, I think it was 10, but let me make sure. The inner row of animals is 10 feet from the center. Look at that, I can't remember things. All right, so the 2.5 revolutions a minute, still our starting point. I cannot get these bars straight today. Out of revolutions, but this time into the circumference of the inner row. So if the inner row's radius is 10 feet, the inner row's circumference is going to be 2 pi times 10 feet. So now we're in feet per minute. So doing our exact, we've got our 2.5 times 10 times 2 gives us 50 pi feet per minute. All right, so the difference in feet per minute of the linear speeds of the outer and inner rows to the nearest tenth difference is going to be outside minus inside. So I'm just going to put out minus in, which is going to be, ours was 100 pi for the outside, minus 50 pi, which obviously is 50 pi, but again, it says to the nearest tenth. So 50 pi to the nearest tenth is 157.07. So 157.1 feet per minute is how much faster, because it's positive, that the outside row is having to go compared to the inside row. So if you think about that, that is why, if I know they have taken a lot of them down because they're dangerous now, but in the old school playgrounds, the little metal spinny wheels that were really hot, that's why it was very easy to stand on the inside of it because you weren't moving very fast, linearly speaking. But when you stood on the outside, it felt like you were going to fly off. And in a lot of times you did fly off because you have so much more linear length to cover on the outside than on the inside. So it is harder to hang on the outside of something circular. Okay, angular speeds. Anyways, rambling there for a second. All right, let's go look at the angular. I'll do this in a different color. All right, angular. So outside, still that same starting point, the 2.5 revs every minute. So I still need out of revolutions. So they're going on the bottom. But now I'm going into degree or radian. I like radians because they're unitless, so I always go into radians unless I'm forced to go into degrees. And that will get us our angular speed for the outside. So 2.5 times 2, we'll leave it. It doesn't say to give this answer exact or rounded, so we're just comparing to see what happens. So we've got our 2.5 times 2 gives us 5 pi radians per minute. So that's how many radians we've got to cover in the outside row. For the inside, 2.5 revs in a minute. And then again, goal is out of the revolutions, but going into angular wise speaking, I guess would how you say it. Just because I'm on the inside doesn't mean I have to go further. I'm still covering 2 pi radians, so I am going to be covering angular wise the exact same amount, 5 pi radians per minute. So angular wise, there is no difference between the outside and the inside. Distance wise, there is a huge difference because one has more distance to cover. Again, if you think about it, if you spin around in a circle, you covered 360 degrees. If you go around a 5-mile circular track, you still covered 360 degrees, but you ran a whole lot further linear distance wise. So that's the big difference in the two. No matter where you're standing, there are 2 pi radians in one spin, there are 360 degrees in one spin. But if you're standing at a point where the radius is 5 feet versus the radius is 5 miles, it's going to take you a whole lot longer to go around one than the other. That's another reason, if you think about track or if you ever ran track, that's why the starting blocks in each lane are staggered, is because the outer lane has a lot more distance or more meters to cover than the inside lane. And that is the end of the first section. So review the notes, check the completed notes if you need to reference anything, and go complete your homework. Let me know if you have any questions.